Good morning. We started already crude oil emulsion treatment from week 5, and week 6 also we are continuing. So week 5 we have seen this gun barrel and heater treater and electrostatic separator system. Now in this week, like 6th week, we are discussing about more sizing mathematical calculation part. So last week we have seen this basic formulation. Now today I will try to do to solve some problems related to this sizing and heat calculation related to this heater treater and gun barrel, horizontal and vertical separators. Let's see what are the things are there. So last week you have seen, last class you have seen this formula to calculate sizing like D and L, LEF, effective length or diameter of the separator. So the formula you can recap just DLEFF for horizontal separator, because we will be using this formula. Okay, so just for recapping purpose I am writing horizontal separators DLEFF because 438 QO oil flow rate, mu O viscosity of oil, del SG specific gravity difference, and dm square particle size diameter, that is will be in micron. So you should remember the units, D in inch, LEF in feet. Okay, this in inch, so mu in CP, dm in micron, del SG already it is unitless, and QO oil flow rate. Okay, so vertical separator. Now vertical separator D equals 81.8 QO mu O del SG dm square. Okay, so this is having power half. In previous case there was no power. Now gun barrel, if you have the formula, just small modification will be there, 81.8 QO mu O. Now you are adding one term called short circuit factor. Okay, last week last class you have seen short circuit factor, del SG dm square. Okay, so the power will be again half. Now some more formula for retention time. Retention time formula for horizontal, TIME. For horizontal again, okay, so you should not mix up this horizontal vertical, otherwise your answer will not match actually. So for horizontal separator, the retention time formula is D square L effective equals Q oil flow rate TRO 1.05. Okay, now for vertical vessel, the formula changes like this: D square H equals TRO QO 1 2. Okay, so and if you are using gun barrel, the formula will be little bit modified. I already told, D square H equals TRO QO 0.12. So TRO unit will be in minute. Okay, and F will be coming for gun barrel because short circuit factor will be coming, and Q is the flow rate, you already know. So you have to check the units also whenever you are calculating. Okay, some more formula there. Some more formula there for this diameter 1%. Okay, for diameter for particle for 1% oil, 1% water, 200 viscosity power 0.25, and criteria is that mu oil viscosity should be less than 80 cp, and dm 1% equals 170, not 1.75, 170 mu O 0.4, and this criteria is 3 cp to mu O 80 cp. Okay, this is the criteria you have to fulfill. And one more formula was there, dm by dm 1% equals water cut power 0.33. Okay. So, this formula, some of the formula will be using, some of the formula we may not use, but in exam purpose or other purpose we can use maybe. So, just you should remember the formula. Okay. Okay. So, viscosity with temperature relationship, there will be chart or table. So, here this table I have drawn from the formula. Formula is like this: viscosity and temperature relationship. Mu equals 10 power x minus 1, and this is given, this formula is given Arnold book, Arnold and Morris book, okay, volume 1. Okay, so I think chapter 2, volume 1. I think chapter 2, I think just you can check. Okay, y equals 10 power z, x equals y into t power minus 1.163, and z value 3.0234 minus 0.0203 g. G is equal to oil gravity. Okay, this is degree API. Okay, so just solving using these equations, I have drawn this figure or this chart. You can see if you are increasing temperature, your viscosity is going down. Okay, so you can use this chart or this figure for your next calculation. If in exam maybe I can give this figure and I can ask, take viscosity from the figure based on your temperature and your API gravity, and API gravity for different API also I have drawn. Okay, so if some, let's say instead of 95 and 100 I have given 98, so just you have to interpolate and you have to get that value for viscosity for specific oil. Oil means like is heavier zone or it is lighter zone. Okay, heavier zone means nearby 20 and lighter means 35 or more. Okay, so normally all oil will be this range. Okay, but if it is heavy or very heavy or ultra heavy, then API will be much lower and lower. Okay, in many problems normally I give viscosity value with temperature. If I am not giving, maybe I will give the chart, then from chart you have to calculate. I will not ask you to remember all this small digits. For example, z equals 3.0234, it is very difficult to remember. So, maybe I will try to avoid to give this formula. Okay, but you should remember like a relationship, mu equals 10 power x minus 1, simpler relation you can remember, but big constants maybe I will give. Okay, for example, if I whole problem I can give the z expression, other expression maybe I can omit. Okay, so that in that case you can remember like 10 power x minus 1, this is a small thing you can remember, fine. Or maybe I will give this whole chart or this figure, then I will ask, okay, take figure data, viscosity data from this figure, or maybe I will give viscosity values. Okay, just try to calculate something. Calculate the size and heat requirement of a horizontal heater heater for the settling or coalescing section. The data given: oil flow rate QO given. Okay, inlet BSW, water content actually basically. So 15% is there. So after separation you are getting 1%. Okay, electrostatic separator heater heater you are getting 1%. Oil specific gravity is given here 0.86. So instead of giving 0.86 I can give API gravity also. Okay, so in that case you have to convert API formula you have to use. Oil viscosity I have given for this 85 degree, 105 degree, 125 degree. Water specific gravity 1.06 I have given. Specific heat of oil 0.5. So many cases if I can ask you assume specific heat, so you should assume 0.5. Okay, you should not assume more than 1 or something, so which will be infeasible. So I will ask select suitable value. Suitable means it should be more closer related to 0.5. Okay, water is 1.1 or 1, that is okay, within that range. If I ask you select suitable value, okay, if I am not giving and I am asking, many time in exam I ask, okay, assume suitable value. So I'll see whether you are having that idea how much will be feasible range. Okay, so within that feasible range you should guess. Inlet temperature 85 degree. Okay, you see this 85 degree, actually this is your operating temperature also. Okay, fine. So fluid inlet temperature higher, but operating temperature will be lower. Okay, because our inlet fluid will be having lower temperature, so after mixing up it will be lower temperature. So treating temperature say 105, 125, no heating. No heating means like 85 degree. Okay. Assume oil viscosity 105, 120, 85 are this 10, 20 and 45 degree. Actually I should write respectively. 85 will be lower, 105 will be higher, lower viscosity. Okay, I should write respectively. Okay, heat loss we are assuming 10%. Okay, now we will try to solve the problem. So first we have to use this equation, dm equals 200 mu power 0.25. Okay, because particle diameter is not given here, so you have to find particle diameter from viscosity. If I am giving particle diameter, then no need to calculate this one. Okay, so for 125 degree Fahrenheit, okay, for different temperature different diameter will be there. Okay, because viscosity related to temperature. So this value will be coming 200 into 10 power 10 0.25. So it is coming 356 micrometer or micron. Okay. Now T equals 100, 105 degree Fahrenheit. So in that case dm again 200 into your viscosity changed to 20, again power is 25. So this will be 423 micrometer. And T when it is coming 85 degree, the viscosity is higher. Okay, mu is 45. So dm equals 245 0.25. It is giving 518 micrometer. Okay, you see the temperature changing, so your particle diameter also changing because viscosity is getting changed. Okay, so ignoring the effect of temperature of specific gravity, so we are assuming specific gravity is not getting changed. A small change will be there, but we are just ignoring. Okay, so for T equals 125 degree Fahrenheit, what is the DLEFF? Okay, the formula you can remember 438. Okay, this is horizontal separator. So fluorate oil mu oil del Sg dm square. Okay, so this will be giving 438 into 7000 already given in the problem. Mu or 10, then del Sg 0.2 actually. How I am getting 0.2? You can make minus of this one. Sg oil minus Sg water minus Sg oil equals actually to come 0.2. Okay. So 0.2 we have put, and dm already we got the value 356. Okay, so this is giving 1212. What will be the unit? Unit will be like inch and ft. Okay, because d and LEFF multiplied. So d unit is inch, effective length unit is feet. Okay. Now for 105 degree, this is for 125 degree. Now if I calculate for 105 degree Fahrenheit, so DLEFF again it will be coming different value. Okay, so 438 again into flow rate, you know, 7000, 700 or 7000. This is 7000, right? 7000 BOPD, barrel of oil, into 45 already. Why 45? Viscosity 105, viscosity should be 20, not 45, 20, and del Sg you are not changing with temperature, so 0.2, and dm value you got for 105 423. Okay, so this value is coming 1714 inch feet. Okay, inch dot feet they have written. Okay, and if I calculate for 85 degree, so DLEFF effective length, so this will be coming 438 into 7000 again into 45, because viscosity will be higher, 0.25, you are not changing as G, DM changed actually, if you see 518 it become. Okay, so this value will be coming 2571 inch feet. Okay, now you use relationship for retention time. For retention time calculation, you can see this d square LEFF formula is there. Okay, just or the formula I have written, you say d square LEFF. So flow rate QO TRO 1.05, 7000 into TRO is given 20 minutes. You see the question, retention time is 20 minutes is given. So 1.05. So this value is coming 1.3, sorry, not 1.33, 13333. So many threes are there, 1 2 3 5 threes are there, inch square into ft. Okay, d square is term is there, so it will be inch square. Okay, now we'll go to the next part of this one, same problem. D value will assume. Okay, initially we'll assume D value. So which range? Like so, they in the book they have taken 60, 72, 84, 96, many values they have taken. Okay, up to 156, and they have made table like this: D and LEFF, and this one is taken from retention time formula, d square LEFF formula. Okay, then LEFF calculated from for 85 degree, for 105 degree, then LEFF 125 degree. Okay, now many values of D they have taken. So for our simplicity, we are taking only one value now. Let's say assume 84. Okay, so 84 corresponding LEFF value from that formula actually will get LEFF equals 13333, 5 3 should be there, 1 2 3 4 5, then D square. Okay, so D square value 84. If you put 84, LEFF value will be coming 18.9 or 19, you can say. Okay, similarly for 85 formula, DLEFF value we have 2571. Okay, so LEFF equals 2571 divided by D. Okay, so from there, if you put D value 84, 2571 divided by 84, the value will be coming 30.6. So some approximation error may be there, so you can get little bit more or less, but should be like 30 around. Okay, it should not be too high or too low. If it is too high, too low, then there will be some error, maybe in my calculation or maybe your calculation. Okay, so 30.6. Now if I go for 105, same data we calculate, LEFF 85. Okay, this one for retention time, and this is for 105, 125. Okay, 105 LEFF will be 1714 divided by 84. Okay, so you are getting 20.4. Then 125 you are getting 14 point. 125 you are getting 1212 divided by 84 equals 14.4. Okay, this value you are getting. This will be in feet actually. Okay, Now this value is 20.4, this is 14.4. Now you can calculate other values also, for example 132, okay, many other values also you can calculate. But then what is the purpose of the calculation? So they have given one chart actually from there. So from retention time chart, this will be length, this will be diameter, 0 to 50, so linear scale actually. 250 means 250, 100, 150, 200, okay. 0 to 45 they have taken. So 0, 45 means 5 into 9, 5 into 9, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, okay. So total 9, just approximately I am drawing. This is a linear scale. So LEFF in feet, D in inch, okay, and this is retention time calculation, okay. So retention time curve first you draw, okay, from D square LEFF equals some value, like here in this case you are having 13333, right? So you got this curve, this is exponential curve, right? Now you draw other curves also. So other curves they have drawn like this. So 85 degree Fahrenheit, some curve came like this, 125, some curve will be like this, maybe 105. So they are saying, so this is the infeasible range, this area is infeasible, okay, this is infeasible. So any data coming above this curve, this retention time curve, there is feasible range, okay. And diameter, if you are increasing diameter too much, separation will not help, okay. So diameter should be like within this zone will be okay, okay. This can be like, for example, this one can be diameter, okay. So in this book they have taken like 20-inch length, 20 feet LEFF, and has taken 84 inch dia, okay. Because this if you are changing diameter too high, possible, but that will not help much, okay. Or if you are going to infeasible region, this below part, this part is infeasible region, so then it will not help, okay. So you have to get the values more than the retention time curve, fine. So this is calculation for horizontal separator. Now we will go for some calculation for heat calculation for this specific design, okay. Heat calculation, 10% loss is there, okay. We have done some calculation in previous lectures also, but for this specific purpose, heat is Q formula, you can remember, 1 by 1 minus loss 15 QO del T gamma oil C oil plus water percentage, then gamma water and C water, okay. Gamma means specific gravity, okay. Gamma is specific gravity of oil, okay. C specific heat, and W water percentage of oil or water particles, how much percentage of water is there, okay. Here you have actually in problem 15%, okay. So your formula, your data will be like this, 1 minus 0.1, because 10% loss is there, this is 10%, okay, into 15, oil flow rate 7000, gamma O, that is given 0.86. In problem you see gamma O is given 0.86, specific heat also given 0.5, I already told, that is feasible range, right, plus water percentage 0.15, you can see BSW given, okay. So we are not we are assuming basically water, because so 15% water is there, and gamma oil gravity is given 1.1, okay, not 1.5, 1.1, and specific heat is given, sorry, gamma water is 1.6, gamma water is 1.06, okay, into 1.1 for specific heat of water, okay, this is specific heat, okay. So finally this result, this will be coming 1.1411433 British thermal unit divided by hour per hour. So in this problem actually I missed something, delta T. Delta T is 105. We are assuming 105 your operating temperature and 85 your operating temperature 85 and your inlet fluid temperature is 105. Actually we are assuming this is an optimal. So in problem if I give, okay, take this one as an inlet flow rate, then you can take, otherwise there are some procedure to find it. So better you assume that, okay, this one your optimal flow rate. Okay, in question, if I give for exam, so in that case I will specify which temperature you have to take for this delta T, okay. Otherwise many students will be taking 85, some will be taking 125, then there will be different answer, that will be a problem. So if I am creating gate like question paper, then in that case multiple answer will be coming. So just to avoid that confusion, I will be giving something concrete which will give only unique value, okay, that unique value will be easier to evaluate. Thank you very much.